it's a bit challenging with the sort of medium. But if you have a question, I don't know how it'll work, but just jump up and down or yell at Sam or something, and I'm sure it'll work just fine.
Yeah, absolutely. They can just come up to the lectern.
Okay, sounds good. Well, I thought I would just give some, sort of personal reflections on some of the challenges and opportunities in computational volcanology. And I was kind of reflecting on this last week. I was at an engineering conference and just thinking about how challenging our problems are in volcanology. In particular, the conference I was at, we were looking at mostly systems that are really well described in terms of boundary and initial conditions to things that we have really hard time defining exactly in our systems. So we have a challenging problem, and I guess we just acknowledge it up front, and that's what, of course, makes it interesting. What I'm going to do today, here we go, is kind of talk about some of the bigger challenges and some approaches that my group and others that I've worked with and other things that I've seen have approached these various problems. I will say though, focusing on the challenges, is important because that's where we have to spend our time. But there are a lot of really exciting opportunities right now as algorithms get better and as computational abilities get better. I think there's a greater opportunity to interact with different sorts of data sets, and probably more than any time, certainly in my career, we can start to, modelers aren't really on the island, right? We're interacting with various folks, and I think also the interdisciplinary training is getting better so that people are trained in computational skills, but also have various other skill sets. Okay, but so what about challenges? So I kind of listed a few here. This is definitely not a comprehensive set, but one challenge, of course, is how do we compare observations to modeled systems, and that's challenging in volcanology because we don't always have the observations that we might want, and they're certainly they're not always consistent in time or in space, and so that's not super trivial. Sometimes we're not really certain what physical processes are occurring, and this is a big challenge. If we can't write the equation, how do we deal with that? And of course, even if we do know all the processes and we can write the equation, can we resolve them in any sort of computational system? One strategy for doing this is to break things into different scales, but how do we deal with those different scales? If we're looking at a volcanic system or a plume, like there on Mount St. Helens on the right there, we might be interested on some physics going on at the size of an ash particle. But then we might also be interested in where that ash goes over hundreds of kilometers away. So how do you deal with that? And then also we have to think about what sort of models are useful under various real world constraints. And we can apply a lot of computational power to certain problems if we're just trying to understand maybe a physical process. But that same model is not going to be very useful if we're trying to do some rapid response or consider hundreds or thousands or millions of scenarios. So what I'm going to do today is just kind of go through talk about these problems in the context of a few examples, and I'll illustrate that a little bit better in the next slide. But I'll talk about them kind of in the context of a few, what are actually quite different sort of systems, right? Magmatic systems where we're dealing with crystals and melt and bubbles, and then eruptive systems where we're dealing with mostly plumes and PDCs in this talk, PDC being pyroclastic density currents. And so we'll talk about both the eruptive products and some of the magmatic products, so low Reynolds number flow and really high Reynolds number flow, and some various different strategies to deal with these. So I'm going to kind of work in this talk from the magma reservoir out to pyroclastic density currents, and so I kind of listed his as critical moments, and there are various critical moments, but these are kind of interesting ones I think for modeling to approach, and something that I think modeling can give a lot to these systems, in part because a lot of these things we can't directly observe very easily. We might see an eruptive plume, or we might see from a distance a pyroclastic density current, but we're not really seeing all the internal processes. And then magma reservoirs introduce a whole another set of problems because most of what we're imaging there is really some proxy, right? We're looking at, in this case, it's a seismic velocity anomaly as a proxy for maybe melt fraction and temperature in the magmatic system. This was from Mount St. Helens. So the idea here is we have some magma reservoir, and then I'm going to kind of follow this up through the erupted plume. I'll talk a bit about acceleration of choke conditions. What's this choke condition, and how can modeling help us start to think a bit beyond some simplifications in that regard. I'll talk a little bit about entrainment and plumes, because that's very important. Sorting of particles, so how do particles separate from the gas in the plume. Talk a little bit about compressibility effects, so shocks, and some microphysical interactions. So this is a problem where you really have to worry about things going on at the scale of a particle, and how does that influence a big scale flow. So in some ways, we might term that the subgrid scale problem. And then I'll conclude with talking about pyroclastic density currents and some of the challenges with pyroclastic density currents, because they contain really vast differences or can contain vast differences in concentration of particles from the bed, which might be very concentrated to dilute clouds above, which are very dilute. Okay, that's where we're going. I'm going to start in the magmatic world though first. And I think what I'm going to do to pose this is I'm particularly going to frame this in the sense of how do we link observations, geophysical observations, and geochemical observations to models. And that's, again, when we go back to that challenges that I listed, the challenging thing there is that we're kind of separated at least one degree from the thing that we're really looking at, because we're looking at proxies of these things, right? We're looking at seismic velocities, or we're looking at zircon age dates, or that sort of thing. But these are some questions here that I think are important, that I think modeling can say something to. What are the proportions and volumes of melt present in the crust through time in an open system with ongoing intrusions? What magmatic flux is required to drive magmatic systems? What controls the lifetime of magma reservoirs? And what proportion of magmatic systems are archived in the crystal record? And again, a large bit of this we can calculate, the thermodynamics, we can calculate dynamics of magmas with some assumptions. But then how do we go from that information, which we've modeled, to something that we can compare to a direct observation, right? A gravity measurement or a seismic velocity measurement. And I'll talk about today, like some secondary models or forward models that take us from magma dynamics case to something that we compare to observations. I think there's a good avenue for this sort of thing, in part because we've gotten a little bit better at understanding some physical properties, but I still think there's a lot of work to be done here, a lot of opportunity. Okay, what about the challenges here? Well, the challenges in magnetic systems is that it's a multi-scale problem again. We have things going on at the scale of crystals and diffusion profiles and diffusion into those crystals and into bubbles. But of course, the whole system might span the entire crust. Some of the physical properties are not fully constrained or poorly constrained. Magmatic processes are sensitive to history and have long memory. So particularly magmatic systems, setting the initial condition is a really hard problem. And we really haven't converged on complete understanding, or at least agreement on small scale physics involved in some of these systems. Is it granular reorganization? Is it compaction, and so on? And of course, there are various range of sorts of models that, and this will be true across every system we look at, right? Where there are different models that have different utility, right? The first here we have sort of reduced dimension or box model approaches. And the idea with this is you reduce the dimensionality and coupling. So you make the equations a little bit easier to solve, and it's very efficient, and you explore a lot of parameter space. And the trade-off there, of course, is you just kind of average over spatial variability. But the great thing about this is you can do lots and lots of simulations to see how the system might behave. And then we can move to continuum approaches, where we're trying to resolve spatial variability. And continuum approaches that can be either single phase or multi-phase. The multi-phase stuff I'll talk about today. The idea with the continuum approach is just that you're treating, it's a bit weird to think about, but you're treating the crystals or the solid also as a effective fluid or continua. And so you're going to have separate continua that you're going to be solving and coupling through drag and energy exchange and so on. And we'll look at that in more detail. Of course, the downside of all this is that you've got a lot more equations to solve, and the computational costs go way up. And so you're going to limit either resolution to a certain extent, or how many simulations you can do. And then going even further, we can think about what about actually directly solving for each crystal, as you might do in a discrete element approach. And in that case, of course, you have, in some ways, very simple physics, right? Because you're just solving exactly what's going on with every single particle. But you have a lot of equations to solve, and it pretty much limits the size of the system you can look at least currently. Okay, so various approaches. I'm going to kind of focus on the middle ground here today for the most part. But even so, you have to make choices and trade-offs. And I'll kind of talk about a sort of a two-part strategy to deal with this. One of which is just kind of look over a lot of parameter space on a crustal scale model, but tries to incorporate thermodynamics so that it can make some comparisons to metrology and melting conditions. And then some more detailed multi-phase dynamics calculations to look at a bit more detail at how melt is separating from crystals and so on, but those are obviously a little limited. I'll particularly talk about today some attempts to look at zircon populations just as a proxy for where crystals might go in a molten system. And zircons are critically nice because they incorporate a lot of radiogenic material, uranium, thorium, and so they can be dated, and that's kind of useful to know how the system has evolved through time. Also gives us some indication of temperature. So in a multi-phase approach, as I mentioned, right, we've got a couple, or depending on, you can have lots actually of different continua. And these are just listing the equations here. I won't belabor this too much, but we have the standard conservation equations. In this case, since it's multi-phase, these little K's will stand for the different phases. I think I did noted that, yeah. And so this phi here is volume fraction. So just basically all the volume fractions have to equal 1. We have a conservation of mass statement with this little R term here. And R term just tells us about exchange of mass between different phases. So it's one way that the phases are coupled to each other. And so if we have crystallization or melting, there'll be terms here. For example, for crystallizing, we'll be taking mass away from the melt and putting it into whatever crystal phase is appearing. And then conservation of momentum, and the big coupling term here is are the drag terms. Also some assumptions that go into the stress tensor. The thermal energy equation, of course, we have phase change being very important here with the latent heat term. And then we also have to kind of keep track of chemical species, silica and so on, as we have the system evolving. And this is largely modulated by thermodynamics modeling. Okay, so what we do is we solve these equations and with some input from some outside models, rhyolite melts in particular, to get some of the thermodynamic information. And the nice thing about incorporating melts into this is that it gives us a nice partitioning of latent heat and sensible heat. So heat associated with temperature change and phase change, and gives us a bit more information about chemistry. And so, the model will tell us, how much plagioclase we have in any moment or something like this. So this is, as you might imagine, a little expensive. So we had to implement this in sort of a parallel computational architecture. I did want to make one little note. So mostly I'm going to be in the continuum domain for these calculations. But for some phases, it's kind of handy to keep track of where crystals might be. And so we solve a Lagrangian equation. Here's kind of a scaled, simplified version here. This V prime would be the particle velocity, and it's modulated by 1 over Stokes number. Stokes number just tells us about the relative response time of the particle relative to the response time of the fluid. So a small Stokes number, as you can see here, will make for a big coefficient before this velocity differential. This is the velocity difference between the fluid and the particle. And so if there's a difference or slip velocity here and the Stokes number is small, it'll cause large accelerations of the particle. And then we have a constant sort of forcing here for gravity. This is a Froude number squared. And so what we're dealing with in these crystals, we have little computational crystals that are flowing around our system. And each of these, we kind of keep track of a little parcel of melt associated with it and diffusion of zirconium into the zircon crystal. And a lot of this is modulated by understanding what the thermodynamics are. And this is kind of first, this sort of approach that what I'm talking about is was first kind of worked on by Ilya Benjamin and Oleg Melnik. But some of you may recognize that this is very similar to what people do with bubble growth too. So some of the bubble growth models from a decade or so ago use a very similar sort of approach. Okay, I kind of think I said mostly that. Okay, other things that we found that might be interesting that I think are still very much in development are taking some of the parameters, right? So this model is producing all sorts of oxides from the model and melt fraction, and from that, of course, you can calculate various physical parameters that could then be forward modeled to think about geophysical measurements. One, more obvious one and easier one to calculate is gravity. Just calculate the different densities and project that onto the surface. Not too hard to do, although it's kind of a heavy-handed calculation sometimes. You can think about electrical resistivity to compare to magnetotelluric measurements. Here you have to, of course, kind of feed in what we know about the physical properties of the material. And there still are, and this is probably true across every domain, but there's still a limited number of experiments to go on here. A few experiments with different compositions that give us some indication of how different compositions might vary, but this set of experiments is certainly much smaller than the set of experiments that might feed into a thermodynamic model like melts. And then you also have, importantly for magnetotellurics, you also have to make an assumption about how connected the melt is, and this is really challenging and a free parameter for most cases because we just certainly don't resolve down to the crystal scale with these models. You can think about the seismic forward velocity models. Again, melt fraction plays a big role there, and probably there could be more experiments done looking at seismic velocities with melt present. But also, of course, seismic velocities depend on what phases you have around too. And there's nice compendium of approaches with Abers and Hacker, for example. Okay, so we're going to do this calculation in a three-dimensional domain. It's kind of a layer cake domain. Modeled roughly on the Andean crust. And our key assumptions here, and assumptions are always important, right? Is that we're just going to think about intrusions from the mantle. These are going to be, dikes that are coming from the mantle into this system. The primary control on the system is going to be whatever that flux is from the mantle, so melt into the crust. It's going to be ongoing, and as extraction is going to be ongoing. And so as the system is evolving, we're extracting melt from the residue, and it can form intrusions higher up that are higher in silica, and it leaves refractory residue. I'm always going to, because I'm using melt, so I'm going to assume equilibrium thermodynamics. So there's no real kinetics going on here. You probably, actually the equations are really amenable to incorporating kinetics, but we just have fewer constraints on kinetics. That's why usually we're assuming equilibrium. The crust is accommodating for these intrusions, so it's solving the room problem, and we have to make some choices on that, like how we're accommodating the melt. And the only kind of real dynamics rule here is that we're not allowing dikes to propagate through high melt fraction melt pools. Basically, fractures will terminate if they encounter high melt fraction. And then from the geophysics point of view, from these forward modeling point of view, we're just going to use phase equilibria to look at the density for the forward gravity models. And I just mentioned that we'll use Archie's law for resistivity. And of course, we can, the thing that we're playing around with, the knob that we're turning here is melt flux. This has been parameterized by various studies. This is a nice study looking at melt fluxes in several different settings, and kind of illustrating, as we go to these sort of higher fluxes here down to some lower fluxes at the bottom here. And these are just kind of looking at crustal thicknesses over time, making some assumptions about crustal erosion and so on. I kind of put the numbers here. One way of thinking about this is the volume per kilometer of the arc, for example, per million years. Because I'm doing it with a 3D model and I'm kind of thinking about flux from the system, I'm going to put this in terms of volume of melt per area at the MOHO per year. And one of the things that goes on with this, and there are lots of different philosophies you could espouse here, but our approach to this has been generally we don't know the detailed history at all of these systems, and we're just going to hit the same system with flux, but having various different geometries. And so that requires lots of different realizations. And so you're kind of looking at a distribution of outcomes rather than kind of a single deterministic sort of perspective. And so again, we're kind of forced into looking at lots of simulations. And I think that's kind of where a lot of magma dynamics work, I think, is going, is to kind of think about lots of different scenarios, because again, the initial condition problem is hard. This is showing a cut of one of these models, just to give you a sense. And it's kind of typical of a lot of these models where we kind of, because we have this kind of extraction step, we often do get a kind of a sort of a warmer region in the center of our domain, usually, depending on how much flux we have. Often we'll have a melt body that develops kind of in the shallow crust, and then a kind of a deeper melt body, mid-crustal to lower crustal melt bodies that develop. And then just kind of showing how this might evolve in terms of composition. So with these sort of calculations, you can develop regime diagrams that look like this a little bit. This was applied to the volcanic system Laguna de Amale in Chile in particular, but you can imagine this being kind of generic too, where we have flux listed here on the left. And so these would be really high fluxes at the top over time. And, you know, these systems, they act a little bit like capacitors. You kind of like, you have these initial intrusions in the lower crust, and then that develops enough melt for it to extract and send melt to the top of the system. And so there's kind of a maturation time in all these kind of calculations, and then kind of gets to, I don't know if it's really steady state, but gets closer to steady state later. And yeah, and so this region down here is kind of typical of fluxes that people think for island arcs. Whereas this top of the system here, we have deformation flux rates that were estimated for Laguna de Amale. And that's kind of where all our calculations are putting us in. This is kind of domain. This is all, this parameter space up here is really consistent with all the products we see at this particular volcanic field. So we can compare the geophysics, we can compare some of the geochemistry, and also these kind of calculations to see what kind of flux rates might be consistent with magma bodies that we're seeing. And I just want to show this again. So, you know, we can take information like this and then apply that to crystal growth models like the zircon growth model. So if I take this thing and I put it into looking at zircon saturation state and zircon growth, you can see a little bit different system here where we're going kind of through time. Any particular location you pick might be undersaturated or saturated. These sort of systems, you have the biggest growth rates at the margin of the system where the largest thermal gradients typically. And Nathan Anderson put this nice graphic together just to look at if you're to pick 1, 2, 3, or 4 crystals here. This is looking at the growth of these crystals and dissolution of these crystals in time as they experience different thermal and compositional environments. And you can imagine doing this for large numbers of crystals to get at population dynamics. And, you know, one of the nice things about this is you can start to play around if into what sort of different measurements might tell us about the system versus the dynamics, right? So we can see where, you know, how larger TIMS measurements might average over some of the things that we may see with SIMS spots but also, you know, dealing with different uncertainties. And so you can start to play games with how analytical uncertainty might lead to uncertainty in different physical processes. So I kind of want to end this sort of magmatic foray and to just talk about some different flux rates and time scales here. And so here we have fluxes. Again, I have this in meter cubed per meter squared per year. And we have things that are relatively efficient at moving around melt. Mixing rate at a high melt fraction can be very fast and have large effective fluxes. But melt segregation might be sort of intermediate. Salt flux from mantle is kind of down in this regime down here. And then if we're like looking about like solid state deformation of the crust, that might be involved like in Rayleigh-Taylor instabilities or foundering instabilities, it goes way down there. Again, just to illustrate that there are just these vast different length scales and time scales involved with this problem, which makes it a rich problem, but also challenging. So just to summarize before kind of going on to some more eruptive things, you know, you can use various realizations to get at intrusion scenarios. And again, here, it's thinking about more like probable outcomes rather than single scenarios that work best with just one case, right? Because with a single flux, we can get various different scenarios just depending on how the geometry of melt intrudes, and we rarely have that information. Or never have that information really in great detail. Upper crustal reservoirs seem to be a nice product given this set of rules that we have, so that they kind of seem to be natural outcome of this set of rules. And I think this illustrates how thermodynamic models and dynamics models can be incorporated with each other to give different ways of comparing models to observations, right? Composition of magmas that make it out to the surface. A nice crystal scale example is our zircon populations, but you can imagine doing this with other crystal chronometers, thinking about diffusion profiles and things like that in other crystal phases. So I kind of want to move from this kind of magmatic world, where a lot of the uncertainty is derived from just knowing where melt is in time, especially deeper time, and knowing really poorly in initial conditions, and also not being able to view directly the system, to systems that are difficult to deal with because they're not extremely frequent, and we have a hard time positioning equipment to view these oftentimes. But think about jets and plumes. So now going from a system where we've gone through fragmentation, and we have a bunch of particles in a turbulent gas phase entering the atmosphere. At least in this case, we have a better possibility of making a little bit more direct measurements, but the physics of the problem are still quite complex, and it's also still very much a multi-scale problem. And so there are complexities with modeling the system too. But I thought I would just kind of orient us with kind of a little bit older approach, but I think a very useful approach. And it's a little bit like, I wouldn't say it's quite like this, exactly like the reduced dimensionality model of the magma realm, but has similar ilk. And this sort of approach, this Morton-Taylor-Turner approach, this is a great paper. If you're looking at plumes, definitely a good thing to read. But this has some assumptions, right? The first kind of explicit assumption here is that the rate of entrainment at the edge of the plume is proportional to a characteristic velocity at that height. So it uses this idea of an entrainment coefficient that I've illustrated with this little flux here. So this entrainment velocity is equal to entrainment coefficient times the vertical velocity. It's self-similar, and it's kind of illustrated in my little sketch here with this kind of V. So the velocity profile is self-similar, and local variations of density are small relative to the background density. Implicitly, it's a single fluid in this case. It's entering into a uniform, stably stratified background fluid, negligible momentum at the inlet here. So we're not worrying about the jet problem, we're worrying about the plume problem here. And it's an quiescent background fluid. And of course, we'll talk about this a bit later, but winds can be important in the atmosphere. So that can play a role in entrainment too. In this Morton-Taylor-Turner approach, I just listed their equations here. R here is the length scale. And so you have conservation of volume, momentum, and conservation of density deficiency, as they would say. And the key here is this epsilon, this entrainment coefficient, is being pretty important to the problem. Woods has modified this a little bit to incorporate a little bit more complexity in terms of energy and buoyancy and non-uniform entrainment. But what these approaches, Woods and Morton-Taylor-Turner illustrate is that certainly getting the velocity at the inlet is very important for setting a lot of the downstream effects of entrainment. And you can kind of see this here in terms of how velocity modulates the height of the column and how there's a sort of somewhat of a bifurcation as we get to higher velocities. So where does that leave us for other computational approaches? Well, of course, all those assumptions we mentioned are simplifying assumptions that make it easier to solve these equations very readily. But what happens when we relax these things? And that becomes important if we want to start to predict, where in the atmosphere ash might go, for example. And so I thought I would talk about this in terms of a series of processes. So here we have, acceleration to choke condition and compressible effects, perhaps later down here. So here the choke just means that we're going to sound speed. Now I want to talk a little bit about that assumption, where it comes from, and what happens when we relax it. And then talk a little bit about some microphysical interactions up higher in the plume. So we might call the subgrid problem again, where we really want to know what's going on at the size of ash particles, because say maybe it's condensing water around it, causing phase change, and that's can be really important for the energy budget and also for particles sticking together. But we really can't resolve individual ash grains in a plume. So how do we deal with that? So I'll talk about some different scaling parameters here. We'll talk a little bit, I mentioned the Froude number before, but particularly Stokes number I'll mention. That, again, that's a particle time scale to fluid time scale. Reynolds number, this is a pretty high Reynolds number flows. And then we'll talk a little bit about Mach number, which is the velocity of the flow versus the sound speed. And sound speed is of course, proportional to the temperature of the gas or the fluid, but it's also going to be proportional to how many particles are involved. So if we kind of use this dusty gas assumption, where we assume that the gas has an extra bit of density associated with particles in it, then that can actually have a dramatic effect on the sound speed as well. So where does this choked assumption go for? It's been a super helpful assumption in any kind of conduit model in volcanic systems, and also plume models, because in many ways it forms this sort of dichotomy between the conduit models and plume models, because it's a nice boundary condition you can set at the top of the conduit or at the bottom of the plume. And where it comes from is just kind of a simplified version of conservation of mass if it's in a compressible system. Here, I just kind of chain ruled it out. So where you see this is 1D. And so you can see how density vary versus Y, area changes and velocity changes. And so that's just a conservation mass statement. We have a kind of a very simplified form of a momentum conservation Euler equation, which we can modify, use the definition of sound speed to write an equation here that tells us how velocity changes versus velocity. And it's going to be 1 over a Mach number squared, negative, times a change of density over density. And if we combine these two, we get this final equation that tells us how velocity changes as a function of area change of our conduit. And what it tells us is if you're really small Mach numbers, so Mach numbers less than 1, so the denominator is positive in this case, in that case, it behaves like our everyday intuition, right? If you have a conduit getting wider, then velocity has to go down because of that negative sign. And if we get a conduit going narrower, then velocity has to go up because of that negative sign. So that's kind of everyday experience. Supersonic flows, or flows with Mach numbers bigger than 1, then we have a negative in that denominator. And in that case, we have the opposite sense, and which is sort of wild, right? Not in our everyday experience, where we have to go at even higher velocities. When you're supersonic, you need to have a widening system. And so this leads to this idea of choke flow, where we're continuously accelerating in this kind of very simplified geometry here. We're continuously accelerating, and we get to a point where we're making Mach 1, so we're moving at sound speed. And to go any faster, we have to have an expansion of our system. And so if it's in a conduit, the conduit has to widen. So the idea is that this would basically place it near the top of our system and separate out the system. And so this just shows how velocity might vary and how pressure might vary in the system as we go across that choke flow condition. And I made a note here that actually mixing in particles has a pretty dramatic effect here. So it kind of sets the sound speed of what's going on at the system, how many particles you can measure. This is sort of the dusty gas approximation. And the fundamental assumption with the dusty gas assumption is that the particles are moving as perfect tracers of a fluid. They're basically becoming a new fluid. And in that case, then you can use this sort of approximation for how sound speed is reduced. And in this case, if X is equal to 1, which is the gas mass fraction, then this kind of reverts back to the kind of standard sound speed equation. Okay, well, what happens, in slightly more complex systems? So if you look at a conduit that has particles that are not Stokes equal 0 particles, right? They're not perfect tracers. And you see in that case, you start to get clustering and pulsing. And, it in general is not far from this choke condition, which is good. But you definitely see variations across that mean. And those variations can be important because they can be propagated into the plume. And this is kind of showing one example of this here, where fluctuations are being seeded from a conduit simulation that has non-Stokes number 0 particles, and that frequency changes the entrainment a little bit. The other nice thing, well, interesting thing at least about these systems is that oftentimes you'll develop a mock disk above, so you'll have a shock. In this region of flow, we have, so this is work from Darcy Ogden a few years back, where we have a overpressurized jet, which wasn't modeled much. A lot of you look at some of the older papers, we oftentimes just use pressure balanced jets, but oftentimes, when we've actually made measurements, we think that in most cases these are overpressurized jets, and so that means pressure is bigger than atmospheric pressure. And then we get these sort of supersonic flows that produce these nice barrel shocks. And that might change entrainment. So Darcy worked a little bit on thinking about how these barrel shocks influence entrainment. It's a really hard thing to see because all these things would be interior of a lot of the ash that we might see. So actually directly imaging these things is a challenge. And getting at these overpressure ratios can be a challenge, but it might have an influence on this entrainment process. And the other thing that wasn't really looked at here, but I think is a rich thing to look at in the future, is just that how the presence of particles that have inertia, how that influences shock structure. And that's a problem that's received a lot of attention in engineering disciplines the last couple of years too. Okay, what about as we relax other assumptions? Certainly, plumes aren't, we can assume they're large scale self-similar, but there's a lot of heterogeneities there. More detailed studies like the study from Andrews and Gardner looked at large scale anisotropic structures, and that's kind of interesting to look at, particularly if you're interested in small scale collapse and kind of hybrid pyroclastic density current plume forming events. Or if you're interested in how mixing is going on in the interior here, what's the thermal structure across this plume? And then, of course, the atmosphere plays a huge role, especially in weak plumes, where winds become very important to setting entrainment. And it'd be great if we could do direct numerical simulations, meaning that we resolve all the different scales of turbulent motion. But on a plume, it's really not tractable to do that any kind of real world scale flow right now. And particles can be segregated into parts of flow. So this is just that Lagrangian equation that we saw before, but you can apply it in this system too. And that gives rise to all sorts of different kind of demixing sort of opportunities, where, Stokes number, where the particle timescales is similar to the fluid timescale, you can start to get demixing and segregation of particles in different turbulent structures. And that, could play a role in things like aggregation and so on. And you can kind of see this in some experiments. So these are some experiments that Yoshi Gilchrist has worked on up at University of British Columbia. And then some simulations that Eric Beard has done looking at a similar set of systems. And what's giving rise to a lot of the sediment waves, as Yoshi calls them, is really kind of a Stokes number phenomena where the particles are becoming segregated in different parts of the flow. And a really interesting thing with these sort of dynamic systems is that you traverse a lot of parameter space. So this is kind of an older engineering based figure, but it's showing basically a Stokes number, two different types of Stokes numbers based upon whether or not you're using the larger scale eddies or the very small scale eddies as setting your time scale. And on this x-axis, we're looking at concentration from really dilute systems to very concentrated systems. And this is telling us something about how particles are influencing turbulence. And so you can imagine at very dilute conditions, it's more like down here would be the dusty gas regime down here somewhere. In that case, we're not influencing turbulence much. As we get to a little bit higher concentrations, we can either enhance turbulent production or enhance dissipation, or taking away energy from turbulent eddies. And then, of course, once we start to have lots of collisions and things, or even sustained frictional interaction, we have this sort of particle-particle interaction dominating momentum transfer. And one of the tricky things for our system, again, when reflecting on how this varies compared to a lot of engineering systems, is that we can traverse any single particle or any parcel of fluid might widely traverse this space. So that makes it a challenge when you're dealing with how to model this and how do you deal with these changes in concentration. And I'd say at this stage, we're still not, very much early days of trying to incorporate this kind of two-way feedback into turbulence and particle-rich systems. And I just also want to mention in this this discussion here is that we have all sorts of rich processes that are going on at the small scale that we cannot resolve with bigger scale models. One great example of this is that ash particles act as great nucleation sites for water droplets. And so, we can parameterize this through experiments like this one from Terry Latham. But, we can't resolve these individual ash grains. So again, there's a large, I think, avenue for lots of experiments and small scale simulations that can then provide information for subgrid models where we don't try to resolve everything, but we try to incorporate the effect of this. And this has been done in lots of different approaches. This is using the Atom model, but just showing how phase change can relatively increase the height of a plume due to the latent heat exchange. Other microscale processes are maybe not important for dynamics as much, but more important for imaging what's going on in a plume. And of course, there's been a lot of interest in volcanic lightning lately. And one of the great interests there is that lightning produces really broad scale radiation in electromagnetic frequencies. And so you can, lightning will produce radio waves and of course all sorts of other waves, but the radio waves are particularly useful because they can be detected at great distances. So we might know eruptions occurring from these radio waves even before we can observe it, if it's in a remote location. And there are various ways to create this lightning. The first step, of course, you have to charge individual particles. And so one way of doing that is by breaking apart things. Another way is by colliding things. This tribocharging just happens with collisions between grains, and they exchange a little bit. It's a little bit like walking across the room with a static charge and touching a doorknob. And then once you get higher up in the plume, you start to get water condensing onto particles and ice forming. And then that's a bit more like sort of the dirty thunderstorm lightning mechanism. But one of the nice things about this is that discharge itself is really modulated by the density of the background gas. And so this is again showing, this plot up here is showing height above a vent, and this is showing pressure. And it's a bit like that barrel shock I was describing before, so that in this case, if we look at this red line, you're overpressurized, and then we actually decrease in pressure above the vent. We actually go under the atmospheric pressure, and then we have a shock that returns us back to atmospheric pressure. And as we go under pressure, we're changing the density and the discharge potential. And so if you follow a set of particles that are charged, they'll reach the saturation curve, which is called a Paschen's curve. And then anything above here, it should be discharging under normal conditions. So you reach charge saturation, and then you start to have lightning discharge. And then at the bottom of this system is where we reach up here, and we reach the shock and go back to atmospheric pressure, and we're kind of quenching it. So this predicts that there should be a lot of shocks leading up to this top of this barrel shock, and that's what's shown here. These are experiments done in Munich of the shock tube, and the idea is that you have an overpressurized vent, and you have a lot of discharges, and that basically can tell you what the overpressure is. Here, K is the overpressure ratio, and these are just various different parameterizations of overpressure ratio, but showing that you have a lot of discharges contained within that envelope. So potentially providing a mechanism to back out what the overpressure ratio is. So I'll just quickly wrap this up so I can have some time for discussion too, because I want to mention PDCs as well. But classic plume theory has been super useful. There are a lot of wrinkles that we need to explore, and there are a lot of opportunities with high performance computing approaches to look at this, and a lot of really big open questions related to how to deal with compressibility effects, turbulent effects, and particularly subgrid effects. Okay, I'll just briefly talk about pyroclastic density currents. So the idea here is that you formed a gas particle rich flow that's traveling under the influence of gravity. It shares a lot in common with other gravity or particle laden gravity currents like snow avalanches and dust storms, but has some more what we might call exotic physics because the gas is buoyant relative to the surrounding atmosphere. So if this thing entrains enough background atmosphere or heats up enough of the background atmosphere and dilutes itself either through that entrainment or for particle settling, it can go through a buoyancy reversal and cause secondary plumes. And even more so than the plume case, we can have wildly different concentrations of granular materials in these PDCs. So the base might be quite concentrated and the top here will be very dilute. And so that modulates that kind of interaction, that particle-particle momentum exchange from the bottom, which might be behaving frictionally or under the influence of pore pressure, because it's so, you've reduced permeability so much, to the top up here, where things are really dominated by turbulent eddies and so on, much like the plume. And much like the other systems we've looked at, there are various approaches, sort of box model approaches, where we use kind of a Froude number front condition to what has been extremely successful depth averaged approaches. And what I think kind of the next wave of things is a lot of like multi-layered depth average approaches. And the nice thing about depth average approaches is that they're computationally, relatively computationally efficient. And so that you can look at lots of different scenarios, and then multi-phase models, a little bit like I've been talking about, where you have particles being separated from the gas. The nice thing that here is you can look at vertical structure. Of course, the downside is that you have to pay a computational cost. And I think one, probably avenue for the future is to get some information from models like this and provide information to multi-tiered depth average models that'll be more actionable. Similar sets of equations. I just wanted to point out here that this is a scaled set of continuum equations. So we have a Mach number, Reynolds number, Stokes number, Froude number, a Peckley number, and this kind of thermal Stokes number. It's kind of a thermal exchange. But I'll particularly emphasize this term here, which is where like all your turbulence assumptions would go. And also it's important where this is where the granular stress closure goes. So whether that's arresting due to friction or other processes, that's included in the stress tensor approach. And this is also where you have to incorporate the effect of turbulence. And any of these models I'll show, they're not completely resolved, meaning that you're not resolving all the small scale eddies. So you have to include some sort of turbulence approach. This is the stuff I'll show here today are using this large eddy simulation approach called WHALE, and this means this wall adaptive type of LES. So basically giving an effective viscosity to account for the small scale eddies. And so one thing we've been, of course, interested in, and I think it's a great development, is how to start to benchmark some of these codes. And one way to do this is to compare it to experiments. This is a experimental facility in Massey in New Zealand. Garrett Lube has put together and colleagues. And its idea is in this big scale experiment, you have heated ash that jumps out of this hopper. It's this ramp, and then because relatively controlled, you can make measurements at different profiles, and it becomes a nice benchmarking case where you compare codes to experiments that are big enough scale that we can have a lot of the dynamics that we might expect at even bigger scales. Of course, there are always trade-offs, and there's some things that this does a better job scaling with than other things. I just always kind of fun to show this video. This is one of their experiments, and you see the hoppers behind you and the flow's coming right at you. And with this various thermocouples and concentration measurements, and here we have a thermal camera offset here a little bit, you can get information about the dynamics of flow and interior concentration. It provides a nice data set. And one thing that really taught us when we were comparing to this experiment, though, is that even small details, if you would say, matter, right? The fact that the walls are of different height in here matter for the simulations. The fact that it goes out of this door into the atmosphere, and there's probably a little bit of background wind, that matters too. I understand that this person volunteered for this duty. I don't think they were con unawares. We have to ask Garrett about that, though. So what I'm going to show real quickly here are a couple of experiments to compare, a couple of numerical calculations to compare to experiments, where we make a few assumptions. We don't worry about the actual hopper drop in these calculations. We take a measured profile from these experiments, and that becomes our initial condition. And then we just compare the downstream evolution. The calculations I'm going to show uses kind of a dynamically scaled particle size, so just dealing with a single particle rather than a full grain size distribution. That's somewhat important. We use density, it's kind of mean density, and the resolution of these is relatively high for us, at least, of 0.015 meters. And so this just shows, hopefully it shows a movie of this, and this is just a cross section of volume fraction. It's a log scale, so these are large density or large concentration variations. And you can see kind of the blues at the top of where it's entraining into the plume as it progresses along. And of course, we want to compare, and this actually does a relatively decent job comparing with the front. As we add in more particle sizes, we find that it actually does a little bit better than this. We think that actually a lot of this mismatch here has to do with entrainment out the side of the system, and then also entering into the outside those doors becomes really hard for us to model because we don't have the background wind measurements to add in. Well, how do we calculate entrainment to, like, say, export this information to like a layered model? Well, we calculate entrainment in this case rather than assuming it. So we create a surface based upon a volume fraction of particles, and we just look at the flux into or out of that surface. And so that depends a little bit on what concentration you look at. And so you could get at different effective entrainment coefficients based on that. But this shows that kind of calculation. Here, red is expansion, so indicating that gas flow is going out of the surface, but the blue is really what we might classically call entrainment. And you see it's quite variable, largely due to large scale structures. And a lot of it we can tell is happening up in this Kelvin-Helmholtz, or the shear instability area. This tells us how entrainment coefficients vary with different concentrations. This would be more like the classic value at really dilute systems, but these other things are nice too. It tells us that that we're having a hard time mixing into the concentrated regions of the flow. And it's not cooling off either because it has to work so much against this density stratification. So this would be a very small entrainment coefficient, whereas up top it's relatively efficiently ingesting gas. And great thing with models is you can like put little passive tracers to see where different parcels of fluid are going. And this is just telling us where this is entraining from. And it's telling us that basically these particles turn red when they're inside the flow. And a lot of it's going on in this sort of Kelvin-Helmholtz instability. So fluid gets kind of shifted back and then entrained along the top here. You can see this also if we put like a layer of a tracer at the bottom here, and it's kind of being swept back, and then after it goes over this head, it's being entrained into the body to a certain extent through these Kelvin-Helmholtz, and a little bit through the plume head or the PDC head. Well, I'm just going to skip ahead just a little bit based on time, but these sort of features do seem to bear out when we look at other systems, natural systems like at Tungurahua, where we have an inhibition of mixing at the bottom in the concentrated regions, and a pretty efficient mixing at the top. And this was work that Mary Benich has done, showing that in the channelized parts of the flow at Tungurahua stays pretty hot because, again, it's hard mixing into that concentrated part of the flow. But where the flow avulses the channel, and it's less concentrated, it's efficiently mixing and actually quite cool. And much like shown in these experiments, they can kind of think about two kind of entrainments. One entrainment that's associated with flow into the concentrated region, what she calls the bed load, and then a little bit higher a little bit more higher entrainment in the dilute part of the flow. Here it's using a negative sign just to note that the normals are going into the flow. Oftentimes classic entrainment coefficients obviously are going to have a negative in it. 0.14 would be kind of the mean of this one, and then 0.06 might be the mean of that bed load entrainment. This is interesting because a lot of the entrainment coefficients we use kind of in our box modeling approaches are based upon earlier experiments, mostly for turbidity current applications. But once we start looking at kind of natural cases and the Paley experiments, they follow a bit higher entrainment curves than we see from these other kind of experiments. And that can have pretty big implications for how these flows evolve, where the liftoff point is, and so on. So that can be, I think, another nice thing to look at in the future. And so I guess the lessons learned for the gravity current piece is that, again, there are a lot of subgrid processes that need incorporated, a lot of which haven't been incorporated in any kind of modeling framework yet. I think there's a lot of possibility to learn things from detailed numerical simulations, particularly when compared to experiments. You see how things are sensitive. It's a bit sobering how sensitive things can be to boundary and initial conditions, but it's important to know. And then I think there's also a great opportunity, this kind of interaction between experiments and simulations to kind of test geophysical approaches. Radar is a great example, or other sorts of approaches to look into PDC, because we have some seismic information, but even interpreting that can be really tricky. And so I think there's, like, again, this great opportunity to really use both experiments, numerical models, and observations to kind of provide another tool to kind of understand or interpret deposits, because oftentimes we're looking at deposits with PDCs. So I think I've covered a little bit of ground here, but I'd happy to take any questions you have. Hopefully I just, this was one set of perspectives, but hopefully it gives you a sense of some of the things we've been thinking about in terms of dealing about some of these challenges, but also hopefully also conveyed that there's a lot of opportunity, and I think a lot of particularly room for growth in the computational sphere with regards to a lot of these flows that I mentioned. And yeah, happy to answer any questions you might have.
Thanks, Joe. That was great. I'm sure there's questions in the room, but I have another question if I can, if I may.
Go for it.
So you mentioned a lot of the kind of more detailed physical models have a big computational costs, and that sometimes may prevent access to some user groups. Have you tried running some of these simulations on the cloud?
We've done a little bit with some of the discrete element simulations. I didn't show you that really here today, but we have done a little bit of that, and that's worked very well, actually.
Okay.
Some of the multi-continuum stuff, there are some challenges, and I think that's mostly having to do with sort of the details of the codes we've been working with. But yeah, I think there's a great opportunity there. I think the step there is more software engineering rather than any fundamental constraints.
Cool.
All right, we got a question here. They're coming to the lecture.
Hi, Joe. It's Cyril.
Hey,
nice
how's it going?
Yeah. Just a question about linking models. You're one of the few that produce different models for different processes. And have you already tried to link some of your models, for example, a Prium model with a PDC model? And if yes, what are the challenges that you encounter when you tried that?
We've done this a little bit. I mean, sometimes we'll do big enough domains where we vary the flux and we get kind of PDCs emerging from a plume sort of source, and that the challenge there is really resolution, because I didn't get into this at all, but for the multi-continuum models, to really resolve frictional interaction, you have to resolve where it's concentrated, because if you have your grid too large, it effectively mixes things, right? And so you're getting lower concentration than would it really be, and that changes the effective viscosity, if you were. And so that the big challenge there is resolution. We've also done a little things recently where we couple conduits to jets, and that's actually very interesting, because most of the conduit cases people have looked at have been steady state, and so this kind of forces you out of the steady state, and you start to see how high frequency forcing and fluctuation causes. And again, I think resolution is the hard part there, because in a conduit you need to be really resolved, but once you get into the plume, you have to start expanding your grid. And I think we haven't done it, but boy, it'd be nice to do a bit more adaptive meshing and that kind of thing with that problem.
Okay, thanks.
We have another question. Someone coming up.
Here. Yeah. Oh. Okay. Hi, I'm Carlos Laverde from Colombian Geological Survey. Thank you for your great presentation. I have a question related to the interaction of the PDC in middle and distal zones with water. Not enough water in order to think in lahars, but enough water in order to think in the conditions of the PDC change with the entrance of the water. I don't know if you know about recent research about this topic, because we want to know when we run a model just like Titan 2D, in what point we need to start to think that the conditions, the rheologic and the physical parameters of the PDC change in order to say, okay, maybe the results since that point are not sufficient well to consider in our hazard assessment. Okay, thank you. This is the.
That's a great question, I think. And there's this rich, I think set of interactions that can occur with interaction with water. We personally looked at, our group has looked at, cases of like PDCs hitting larger bodies of water, like phreatic kind of explosions and that kind of thing. And, in that case, and I think also in the case of even, more subtle interactions, it depends a lot on the permeability of your flow, how quickly water vapor is getting, surrounding it, and also how much heat exchanges are going. So we looked at some of these littoral blasts from Montserrat, and in that case, you did get a big shock coming out of it. In that case, it was really, we thought at least, largely dependent on having a grain size concentration that allowed for efficient heat transfer with the water to produce vapor at fast enough rate to produce this blast. But we did have a set of calculations where it wasn't as efficient and it just kind of bulked up the flow. And so you get a thicker flow and a bit more dilute that's more water vapor rich. And I can imagine even going over vegetation, this could be important. I think the key here is really, for the models, certainly we do, is you'd want to have a bunch of experiments that get at those flux rates, like given a certain thermal energy, what's the input of vapor per time? And if you had that kind of almost like a reaction rate, you could, I think, incorporate it and understand better. But I think there are a lot of, I think there's a great example of a subgrid experiment where, you're thinking about either going over a ravine or even over vegetation where you might be producing some water vapor. It'd be interesting to look at that source. But we haven't done anything systematic, but I think it's a great problem for sure.
Okay, thank you.
All right, any other questions from the room? Do you open check or?
Oh, sure. Joe, that was an awesome talk. Can you hear me okay?
Oh, yeah.
Okay, cool. I have a question. It seems like a lot of the PDC experiments and modeling is devoted to relatively small volume PDCs, and I understand why you would do that. But recently it's been kind of interesting to me because I've seen a bunch of literature on slow-moving, very large volume PVCs. I think there was a paper on the Peach Spring Tuff recently where they were talking about displacement velocities of these caldera-forming ignimbrites of 10 meters a second, or almost like a fast debris flow sort of velocity. Has anybody looked into whether that kind of flow can produce the dilute plume and the turbulence required to produce the dilute plume, and how well they would be coupled with those kinds of velocities? It seems not too intuitive to me to have these slow moving large flows, but I don't know why not. It just maybe it was trained that way.
Right.
Experiments tell us.
No, well, I think it's, I don't think it's, there's tons of parameter space that hasn't been explored. I think the closest that that various folks have thought about this is comparing to some of Olivier Roche's experiments. So these experiments, if you haven't seen them, they're a case where you have a bunch of ash or synthetic material has pretty low permeability, and you fluidize it. So you inject gas in the bottom of it and kind of behind a locked gate, and then you open that gate, and then in that exchange you have flows that go further. And so basically the fluidized flows, because of the gas in them, reduces the friction, and you get longer run-out flows. That can be, they're fluid-like, but they're definitely not, big turbulent flows or anything. Mm-hmm. And I think the inspiration for like that, well, the Peach Springs paper for sure. Yeah, whether or not that would, we've compared, so we've done some benchmarking on Olivier's experiments in particular, just to get the rheology right. but I don't, you know, and then we've had some moderate scale simulations looking at flows that have that kind of fluidized base. I don't know if we've ever looked at any that are quite that slow as anything like that they were predicting for the Peach Spring stuff. And, you know, it's tricky. Yeah, it's totally possible that you would do that, but I would certainly change the entrainment condition at the top. I think you're exactly right. But maybe that explains, you know, one thing you probably grapple with this too, is let's say these high grade ignibrites, the Snake River Plain. And so these are ignibrites that were initially even mapped as lava flows because they're like so hot and rheomorphic. And so they clearly stayed hot for long distances. And I remember when somebody first explained this to me, I was like, well, why isn't it, you know, if it went that far, why didn't it entrain all sorts of air and cool off? But maybe this is one explanation, right? That it didn't go fast, it didn't entrain, and it just stayed fluidized and hot for long distances. I'm not sure. I haven't thought in great detail about that, but
Yeah, it's crazy. Okay, that's cool. Thanks.
Giovanni Pacho here. Just wanted to thank you for a fantastic talk.
oh, thanks.
You did not mention the word uncertainty anywhere. Seriously. What are your thoughts about the model uncertainty? I think we have a bit of a handle on things to do with parameters. Model form, I think we struggle with.
Yeah, this is challenging, and there are various ways to get at this. I think probably nothing perfect right now, but you know, so one way is to try to propagate uncertainty, like for example, like in the physical properties from the magmatic models, you could propagate that uncertainty, and then there's also the uncertainty associated with just the fact that which is harder to constrain, but the fact that, you know, the geometries are poorly known. I guess in that case, we've typically just kind of presented a range and then try to present, you know, a probability distribution, then also introduce, you know, some propagated uncertainty that tells us, you know, whether or not that uncertainty is bigger or not than the distribution of outcomes we get. In terms of the volcanic case, there's maybe, you know, eruptive case, there is greater hope, I guess, because we can measure a lot of the atmospheric parameters. So it's much easier for us to, like in kind of reanalysis format, to think about how, you know, variations in winds and wind input might change the system and propagating uncertainty that way. But there's some things that we're just still grappling with how to propagate uncertainty, and because we haven't systematically measured enough things. So, for example, drag coefficients would be a good one where we think we need to do that, but and we know there's uncertainty associated with that, but we don't know the size of the uncertainty is uncertain. In other words. But yeah, that's where we're at with.
There's a quote. There's a quote.
Yeah.
The size of the uncertainty is uncertain.
Yeah, well, I mean, this is what, you know, was really struck me last week at this engineering DOE conference, was that, you know, we have a lot of one way to go. We have a challenging problem, but we have a long way to go.
All right. Thank you so much. Do we have any lingering questions? If not, all right. Thank you so much. Can we get, you know, one more round of applause?
Well, thanks. It was great chatting with all of you. I wish I could be there.
Well, yeah, it was a great presentation. You really covered a lot, and thank you for answering all those questions in such detail.
Yeah, I guess the last point I would maybe say is that with regard to certainty, I think that's where experiments are super important, you know. So I think because that's where you really have to grapple with it. For example, when we first comparing to Pele, those experiments, one of the parameterizations was a little off, and we kept like having horrible times. And we realized it, like after lots of discussion, that it was just an issue with parameterization. So yeah, so experiments are key, I think. But thanks for listening, and thanks for the questions, and yeah, and the discussion.
Thank you so much. All right, see you. Have a great rest of your day.
Yeah, take care. I'll hopefully see many of you soon.
Yeah, absolutely. Bye-bye.
Bye.